A comprehensive guide to scikit-learn's PLS regression. The PLS regression class in scikit-learn implements partial least squares regression (PLS), a powerful technique for predicting a dependent variable from one or more independent variables. When both sets of variables are potentially highly correlated and multicollinear. Unlike ordinary least squares (OLS) regression, PLS does not directly model the relationship between the dependent and independent variables. Instead, it extracts latent variables components that capture the shared variance between the predictors and the response variable. This makes it particularly well suited for scenarios where the number of predictors exceeds the number of samples. Predictors are highly correlated. The data exhibits nonlinear relationships. Understanding the mechanics. 1. Latent variables. PLS seeks to find a set of latent variables that explain the maximum variance in both the predictor and response variables. These latent variables are linear combinations of the original predictors and response variables, respectively. 2. Singular value decomposition (SVD). The core of PLS lies in the SVD of a cross-covariance matrix between the predictor and response variables. The SVD extracts the principal components that capture the maximum shared variance between the two sets. 3. Projection and regression. Each latent variable is then used to project both the predictors and the response variable onto a new space. This projection reduces dimensionality and eliminates multicollinearity. Finally, a linear regression is performed between the projected response variable and the projected predictor variables to obtain the prediction model. Key features of PLS regression in scikit-learn. 1. Construction. N components determines the number of latent variables to extract. A higher number can lead to overfitting. Scale. Whether to scale the data before applying PLS. Scaling can improve model performance and stability. Copy. Whether to copy the data before processing. Maxiter. Maximum number of iterations for the PLS algorithm. Tolerance for the convergence criterion. CV cross-validation strategy for model selection. 2. Methods. FitX. Y fits the model to the data. PredictX predicts the response variable for new data. ScoreX. Y returns the coefficient of determination R squared on the given data. TransformX transforms the predictor data to the latent variable space. Inverse TransformX reconstructs the original predictor data from the latent variable space. GetParams returns the parameters of the model. SetParams sets the parameters of the model. 3. Attributes. X weights for the predictor variables. Y weights for the response variable. X loadings for the predictor variables. Y loadings for the response variable. Regression coefficients for the final prediction model. N components. Number of components actually used in the model. Y scores for the response variable in the latent space. Applications of PLS regression. Spectroscopy. Analyzing spectral data for predicting material properties. Chemometrics. Modeling complex chemical systems and processes. Bioinformatics. Analyzing gene expression data and predicting disease outcomes. Finance. Predicting financial market trends and risks. Marketing. Understanding customer behavior and predicting product sales. Advantages of PLS regression. Handles multicollinearity effectively. Deals with highly correlated predictors. Reduces dimensionality. Extracts latent variables, reducing the number of variables to consider. Nonlinear relationships. Can handle nonlinear relationships between predictors and the response. Interpretable results. Provides insights into the relationship between variables through loadings and weights. Disadvantages of PLS regression. Parameter tuning requires careful tuning of the number of components and other parameters. Overfitting risk can overfit the data if the number of components is too high. Limited interpretability. Understanding the exact relationship between variables can be challenging due to the latent variable representation. Choosing the right number of components. Cross-validation. Using techniques like cross-validation to assess the model performance for different numbers of components. Scree-plot. Visualizing the variance explained by each component. The elbow in the plot can suggest an optimal number of components. RMSEP. Root mean squared error of prediction. Monitor the RMSEP for different numbers of components and choose the value that minimizes the error. Example: predicting wine quality with PLS regression. Python. Import pandas as PD. From sklearn, cross decomposition. Import PLS regression. From sklearn, model selection. Import train test split. From sklearn, metrics. Import mean squared error. Load the wine quality dataset. Wine data PD. Read CSV. Wine quality red.csv. September. Split into features and target. X wine data. Drop quality. Axis 1. Y wine dat a quality. Split into training and testing sets. X train. X test. Y train. Y test. Train test. Split X. Y. Test size 0.2. Random state 42. Create a PLS regression model with 5 components. PLS regression components 5. Fit the model. PLS. Fit X train. Y train. Predict on the test set. Y PLS. Predict X test. Calculate the mean squared error. RMSE mean squared error test. Y PRED. Squared false. Print fruit mean squared error RMSE.2F. Conclusion. PLS regression is a versatile technique for analyzing complex data with high dimensionality and multicollinearity. Its ability to extract latent variables and reduce dimensionality makes it an effective tool for predicting dependent variables in various fields. However, it's crucial to carefully tune the model parameters and avoid overfitting to ensure accurate and reliable results.